Okay, now for our first funky operation with matrices, and we're going to talk about matrix vector multiplication. This is a really important operation, and it's important to get it down. It's going to form the foundation for when we do matrix multiplication a little bit later. And one of the things that makes it tricky at first is because it's not what you'd expect. Okay, first of all, the thing you get back as a result of doing matrix vector multiplication is not what you'd expect, or at least it's not what I expected. All right, so let me show you how that works. Let's say we have a matrix here, A. And let's make it a 4 by 2. So 1, 2, 3, 3, negative 9, 4, 1, 0. Right? Let's say we have a vector x, and we're going to make that a column vector that has 2 elements. We'll say it's got 2 and 3. Right? Here's what we're going to do. We're going to do the operation A times, and we're going to put the dot there, which looks like a dot product, and it sort of is, as you'll see, but we're going to call it times. A times x. And the question is, what are we going to get back? Now, first of all, we have to ask, under what circumstances can I actually do this? And then the second question is, what kind of thing am I going to get back there? And here's the rule, and this is what you got to memorize, and it'll make sense eventually, but at first it seems kind of arbitrary. What we're going to say is, if the matrix is m by n, then the vector you multiply it by has got to be n long. Or if you think about it as a column vector, it's n by 1, right? So really this is an n by 1 matrix, as we've said, right? Because you're basically saying it's got one column. So if the matrix is m by n, then the column vector has to be n long in order for this operation to even make sense. That seems weird. The number of, remember, that's the number of columns that A has, right? The number of columns that A has to equal the number of rows that X has. And in this particular case, that turns out to be true because n is 2 for this matrix. This is a 4 by 2. And we've noticed that this is a 2 by 1 because we're sort of treating it as a degenerate matrix. Therefore, this operation does make sense and we're happy. If it's anything else, we can't do it. If I had given you a 3 by 1 and said, hey, now what's the multiplication? Can't do it. If I'd given you a 4 by 1, can't do it, which seems weird because you're like, well, wait a minute, there's 4 rows here. If I give you a vector with 4 rows, you're telling me you can't multiply them? Yes, that's what I'm telling you. You can only do it if the number of rows of X is equal to the number of columns of A, weirdly. Okay? Now, question, what do we get back at the other end? And the answer is, we're going to get an m by 1 answer. So in this particular case, we are going to get a 4 by 1 when we multiply our 4 by 2 times a 2 by 1. Now that seems so weird to me because it's like, wow, we don't even have a 4 by 1 thing on either side of our multiplication symbol, right? Where did a 4 by 1 come from? We don't even have that. Yet, nevertheless, that's what we're going to get out when we take a 4 by 2 times a 2 by 1. We get a 4 by 1. Who knew? And here's how you compute it. So I'll make my 4 by 1 entry. And then what we're going to do is take this row times this column. And when I say times, I mean the dot product sense. So I'm doing 1, 2, dot producted 2, 3. Okay, you kind of have to turn your head 90 degrees to see that. But if I do this dot product, remember that's 1 times 2 plus 2 times 3, which is going to be equal to 8 if I've done my math right. So 8 is going to be my first entry there. And then we're going to take the second row times this thing here. So now we're going to get 3, 3 times 2, 3. And when we do that, we're going to get 3 times 2 is 6, plus 3 times 3 is 9. 6 plus 9 is, I believe it's 25. And we're going to keep doing that for every row here. Negative 9, 4 times that thing. So now we get negative 18 plus 12, which is negative 6, I believe. And then we're going to take 1, 0 times that, which is going to give us 2. So that turns out to be my answer. Okay? Seems totally weird, and for right now, you wanted to sort of memorize that that's the truth, okay? And then we'll see why that is. Now, here's where you're going to kind of get some intuition about this, hopefully, and we're going to see a couple reasons why this would be a useful operation. Turns out to be incredibly useful, all right? I want to suggest that there are 2 different ways to think about the matrix vector multiplication. 2 different ways, and you need to understand both of them, all right? So here's 2 ways to think about taking a matrix and multiplying it by a vector. The first one is exactly what we did operationally, okay? we took all of the dot products. We took the dot product of that vector x with each of the matrix's rows, and we ended up getting back a vector that gives us the value of that dot product for each of the matrix's rows. So clearly the answer we have to get has to have as many values in it as we have rows in the matrix, right? Because that's how many different dot products we're doing. And clearly the length of each row in A has to be the same as the length of the x vector, otherwise we can't even do the dot product. So that's why those two dimension constraints are there, right? So that's the first way to think of it. Now, that turns out to be the right way to think of it about 40% of the time. It's very, very useful. About 60% of the time, this turns out to be more useful. And like I said, you need to understand both. What we're getting here is a linear combination of the matrix's columns. So remember, a linear combination is basically when we have a bunch of different vectors and we multiply each one by a coefficient and then we add them up together. So we're treating the columns now as the things we're taking a linear combination of, and then we're getting that sum of those matrices columns, each of which is multiplied by a coefficient, and the coefficients are in the vector x, and we're adding them up all together to get the thing, right? Now, it's not obvious that you would even get that, but let's convince ourselves this is so. So if we go to our example, let me just start again with a little bit of a newer one. I'm going to make a little bit wider matrix this time. 2, 4, 9, 3, 1, 7, 1, 2. And let's multiply that by x. And again, we know that x has got to be the right dimensions. We know it's got to be a 4 by something, right? Because this here is 4 long. Therefore, our vector that we're multiplying by had better be 4 tall. So let's say we've got 1, 0, 1, 2, right? Now, what I'm going to claim is that if you look at the columns here, and consider each one of these columns a two-dimensional vector. So we've got 2, 1, 4, 7, 9, 1, and 3, 2. But what I'm really going to get when I do this is I'm going to get 2, 1 times 1 plus 4, 7 times 0 plus 9, 1 times 1 plus 3, 2 times 2. Now, where did I get these numbers? Well, I got these numbers from this vector. This vector x is giving us the coefficients that we're multiplying each of these dominoes by, each of these vectors by, in order to get the answer, right? So if we compute it this way, just to see what we get, 1 times that is going to give us 2, 1. 0 times this, of course, is going to give us 0, 0. 1 times this is going to give us 9, 1. And 2 times this is going to give us 6, 4, right? I think you'll agree that I've just done the multiplication out of the coefficients here. And if I add all those up together, I'm going to get 9 plus 2 is 17, and I'm going to get 4 is 6, right? So that's going to be the answer that I would get if I did these linear combinations. Now, let's see if we get that, if we actually do the multiplication the way we learned how to crank it out, right? So we're now going to take this row, dot producted with the vector, and so I'm going to get 2 times 1 plus 4 times 0 plus 9 times 1 plus 3 times 2. If you add that up, you get 9, you get 17. And that's going to be the first element in my answer. And then secondly, if I dot product here, I'm going to get 1 times 1 plus 7 times 0 plus 1 times 1 plus 2 times 2. And that's going to end up giving me 6 there, right? And so clearly we do get the right answer. Stephen never lies. And so you can kind of see why that worked, right? Because when I multiplied this out and sort of spelled out what we're doing here, we're doing the same thing as we are here. The only difference is here we were sort of treating it a whole domino at a time, whereas here we were treating just the top half of each domino and then the bottom half of each domino separately. But it turns out to be the same operation when we get this thing over here. So, fun fact, when you do a vector multiplication, a matrix vector multiplication, even though you're taking the dot product with all the rows, that turns out to be the same thing as taking a linear combination of the columns, right? Now, let's see why we'd want to think about it in each of these two different ways. It totally depends on the application you're doing, right? So let's take this example here. Let's say I've got Jezebel, and she's on our matchmaker.com thing. And let's say she took our survey And her results were, she said, hey, I love skydiving. I can't stand knitting. I'm okay with, race car driving. Candlelight dinners, not so much, but fun nights at the dance studio, yeah, I did great there, right? Now, normally, of course, get it, we're going to normalize this vector, because as we talked about before, that allows Jezebel to cheat if we don't, right? But just to do this matrix vector multiplication illustration, let's not do the normalization just for the moment, right? Now, imagine if I have all of the possible guys, let's say Jezebel is heterosexual, and so she's eligible to be matched up with all the guys on Matchmaker.com. I could look at all the guys, and I could list all of their survey results. Let's say this first row is Biff, and let's say he answered a 42996 to the survey questions. Next one is Joel, and he answered 221010. Next one is Filbert, and he answered 00939, etc., 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 right? Let's say there's 10,000 guys on Matchmaker.com, and we've got each of their survey answers in this nice little table here, right? So I'm setting this right up for this thing to be useful. Jezebel, we really should put an arrow on her because she's a vector, right? If I take guys times Jezebel, look at what I'm getting. I'm going to think of this matrix vector multiplication in the first way. I'm going to think of it as the dot product of every row with Jezebel. So the first element of my answer here, and by the way, this is going to be 10,000 by 1, right? We know that if guys is 10,000 by 5, and if Jezebel is 5 by 1, then good news, this makes sense. We can do it at all because those two numbers are the same, and the result is going to be a 10,000 by 1, right? So what we're going to get is some number here. I don't know what it is. Let's say it's 42. I'm too lazy to do the math. And then we're going to do Jezebel with Joel. And let's say we get 36. And then we're going to do Jezebel with Filbert. And we're going to get 93. And we're going to do that with all of the guys. And look at what we've got. Isn't this cool? We have now got a record of how good she would be with Biff, how compatible she is with Joel, how much she'd like Filbert, all the way down to our last guy, which is, maybe Weldon or whatever, right? And so what we've done is taken all the dot products, because that's precisely what we want to do, right? Taking the dot product with any one guy, and Jezebel tells us how compatible those two people would be in a date, presumably. So if I want to find out, hey, who are the best dates for Jezebel? Who's the one person who's most likely to be her dream date? Or what are the top 5? Or who's the worst? Or whatever. I can do the whole thing at once by just saying take this whole matrix and multiply it by Jezebel. And we get all those answers at once. That is a situation where it makes sense to think about it in the first way. That's a case where it makes sense to think about it in the all the dot products with the matrix's rows way, because that's exactly what we want to do. Now, let's look at an example where it makes sense to think of it in the number 2 way. Suppose I have this matrix. I'm going to make it a little bit bigger here. And I'm going to call this recipes. Usually we use a capital letter for matrices, so I'll make a capital R, right? And let's say each column represents one ingredient. So this is chocolate chips, and this is sugar, and this is fudge, and this is, eggs. I don't know. And each one of these recipes here, we're going to say, I'm going to make a matrix here called recipes. And I'm going to say that each of these columns here is a recipe. This recipe is for chocolate chip cookies. This one here is for sugar cookies. This one here is for fudge. Last one's for cake. So I've got all the different recipes in my repertoire. And then we're going to say that each row is one ingredient. So we're going to say this first row is flour, and the second row is butter, and the third row is eggs. Last one is chocolate chips. And then, as I'm sure you can predict, we're going to say that the entry of the matrix at a particular row and column is how many of that ingredient is needed by that particular recipe. So we'll say the chocolate chip cookies take 1 cup of flour, and 1 stick of butter, and 2 eggs, and a bunch of other stuff, and 1 bag of chocolate chips. And sugar cookies take 2 cups of flour and 2 cups of butter, and they take 1 egg and no chocolate chips. And fudge takes no flour, but it takes a ton of butter. That's what makes it so good. And no eggs, but a ton of chocolate chips. That's the other thing that makes it good. Cake is going to take 2, 1, 3, 0, something like that, right? All right, so we've got our whole recipe matrix here. And now we're going to make a vector. And our vector, let's call it x, is going to be a column vector. And we know this had better be the same height that this thing is wide, right? So let's say we have, 13 different recipes here. This thing had better be a 13 by 1 matrix, right? Or a 13 long column vector. And this is basically going to say how many of each recipe I want to make when I go on my shopping trip. So I want to make 3 recipes of chocolate chips. I don't want to make any sugar cookies today, thanks. I want to make 2 recipes worth of fudge, running out of room, and I want to make 1 cake, something like that, right? Now, if we bring that up here and do this matrix multiplication, and by the way, I've drawn this a little bit badly because I've made it seem like the height of this is the same as the height of this, and that is by no means the case, right? What's important is that this guy's width is the same as this guy's height. Okay, it's completely immaterial whether or not the height of recipes is the same as the height of the x vector, right? So let's just make that explicit to show. Let's say I've got 13, or how many? Let's say I have 100 different ingredients, and let's say I've got 13 different recipes. So this thing's 13 high. Whereas this matrix is 100 high, right? Okay, so what I'm going to get out of here, as we know, is going to be a 100 by 1. And this is going to tell us how many of each ingredient we need to buy, right? It's going to say, hey, how much flour do you need to buy? How much butter do you need to buy? How many eggs do you need to buy? All the different possible ingredients, all the way down to how many different chocolate chips you need to buy. Right? It's going to say, oh, you need 6 cups of flour, and you need 3 cups of butter, you need 16 eggs, and you need 2 bags of chocolate chips. And this becomes our shopping list, right? And this is perfect to think about in that second way, because if you think about it, what we're doing is we're taking these things right here, which is how many of each recipe I want, and we're using those as the coefficients for this entire vector, and this entire vector, and this entire vector, all the way down to this entire vector, right? Each one of the coefficients of the vector x is telling us how many chocolate chip cookie recipes do I want? How many sugar cookie batches do I want? How many fudge recipes do I want? How many cakes do I want to bake? And that's exactly how shopping lists work, right? Because each one of those recipes requires a certain amount of ingredients, which is given to us by the column in that thing. And so we are precisely taking a linear combination of all of the columns of the vector in order to get our combined shopping list. In this case, it doesn't make a lot of sense to think of it that first way, right? The dot product of this with this sort of is meaningless. That's not really what we want to think of it as. We want to think of it as, I want this many of this, this many of this, this many of this, in order to get our final thing, right? We can also think of another example, just going back to the domino game, right? That's exactly what we had in the domino game. We said, okay, here's our vector, or our matrix rather. Let's say I'm going to give you a 1, 2 vector, and I'm going to give you a 4, 4, right? These were yellow dominoes, as we know. And if I said, hey, a linear combination of those, what if I take 2 of the first one and 1 of the second one? Then I'm going to get a linear combination here where I could do it both ways. Like, first, let's do it this way. If I take 1, 4, and dot product it with 2, 1, I get 1 times 2, which is 2, plus 4 times 1, which is 6. So I end up getting 6. And then if I take 2, 4, and dot product that with 2, 1, I get 2 times 2 is 4. 1 plus 4 is 8, so I end up getting 6, 8. And that was one of our answers, right? But if I think about it the other way, which is really the way you want to think about with a domino game, is I'm specifying 2 of these and 1 of these. It's a little weird because, like I said, you have to get used to rotating your head 90 degrees and kind of getting limber there, right? Because this vector, you want to think of it as sort of turning flat and specifying then how much of each column to give you. And so now we're saying, I'd like 2 of these vectors, and I'd like 1 of these vectors, please. And then doing exactly the same math operations, we discover, that's going to give us the vector 6, 8. And that is exactly what we got, right? So two different ways to think of vector matrix multiplication, or I should say matrix vector multiplication. And it's important to be able to think about both. And again, remember that you can only do the operation at all if the width of the matrix, the number of columns, is the same as the height of the vector, the number of rows in that column vector. And when you get it, you get back a vector of a different shape normally, which is going to be as tall as the number of rows of the original matrix by 1.